Okay, welcome back to Feedback Control Systems. This is Module 8.4, Transient Response and Sensitivity. The objectives of this module are to look at transient response design via gain changes, then look at a generalized root locus, then look at root locus for positive feedback systems. To date, we've just looked at negative feedback systems. We're going to see what special cases happen for positive feedback. And then finally, we're going to end with pole sensitivity. So first, we're going to look at transient response design via gain changes. So in the previous module, what we saw was we said, hey, let's vary the gain K such that we get a certain damping, right? So we drew our damping line, and then we solved for K such that we made sure we were on that damping line. So in that case, what were we doing? Well, once we designed damping, that correlates to percent overshoot. So we can actually look at percent overshoot, settling time, the peak time. We can look at those equations from the previous modules. However, one thing we note was those equations were generated specifically for second-order systems, right? They assumed second-order systems. They also assumed no zeros, right? The general form, and let's not just talk, let's just write that down. The general form of that second-order equation was what? It was omega n squared, s squared plus 2, the damping factor, omega n, times s, and then plus omega n squared. So this was our general second order system, and look, no zeros, second order system. So those were the assumptions by which we were able to come up with things like percent overshoot, settling time, and peak time. So what I want to do is start to look at some of these characteristics and see where we can make some approximations as we have zeros, as we have higher order systems, where we could kind of say, you know what, those second order approximations were good enough, okay? And we can use those, okay? So here's a starting point for us. In looking at the key here, so in black, what we have are our open loop poles. So in this case, we have an open loop pole, a second, and then a third open loop pole, and then you'll see the same ones over on this side again. In blue, X, we have our closed loop pole. So if we start with our open loop poles, we vary our gain K. What's going to happen is they'll migrate, and then they'll go away, etc. And so for a specific value of K, you might see we have in blue these closed loop poles as shown there, or in this case, here. And one thing to talk about is in this example here, we don't have any closed loop zeros as of yet. The next part down, we'll actually see that. So in this case, there are no zeros. And what we'll see is as P3 moves to the left, here's P3. And then in this case, it moves to the left. P3 is going that way as we further increase our gain. As P3 gets farther and farther and farther to the left, that system dynamic is going to be so fast relative to these two poles that these two poles will dominate, and for all intents and purposes, we can ignore P3. Okay? And we had seen that also in previous modules, depending on the location of P3, where we can essentially make that approximation of a second order system or not. Okay? So that's for the case when we have no zeros. Now, in this case, look, we've added a zero. Now, when we add a zero, let's remind ourselves that the poles do what? At the root locus starts at the poles and at k equals 0, and then we'll go to either finite zeros or infinite zeros. So what we'll see in this case, once we've introduced this zero, that's a finite zero. Now, as we look relative to our open loop poles, essentially in the same location, here and here, as well as here. Okay, those are our open loop poles. There's our closed loop zero. And then we are looking at our closed loop poles as we vary the gain. So in this case, these two poles, right, we'll see these two poles, they merge together and then go off axis towards infinite zeros. Okay, zeros at infinity. However, looking at this pole, the closed loop pole, look what it does. It's migrating towards that 0. Okay, and so what we're going to see is the following. With a 0 added, as P3 moves closer to the 0, what's going to happen? Once they get close to each other, you could imagine a 0 here and a pole here. Well, if they're the same value, we can essentially cancel them out, and they can basically offset each other. And so that's what we'll see, is as P3 moves closer to the 0 to cancel it, then what we could do, so for example, in this case, if we say P3 and the 0 are close to each other, then these two, basically, we look like we have a second order system again. We can go back to this, given a desired damping, the overshoot, etc. All those equations will hold. So again, just wanted to bring this information forward, and so we can use this to our advantage to design with some specific transient response goals that we may have imposed on us. So, in terms of a generalized root locus, we can also do this for pole placement. So in this case, we look at our open loop characteristic. It's a second order system. We've already defined one pole, in this case -2, but the second pole we haven't defined, and so here it's at P1. So maybe as we're designing a system, some hardware, an electrical system, mechanical system, etc., we might want to design our plant, if you will, and we might say, hey, where could we place a pole to get sort of the open loop characteristic to be where we want, and then later when we put in some gain, we could basically shape it in a direction that we want as well. So here we have P1, again, H of 1, meaning we have a unity feedback system. We can come up with our loop gain, as shown here. And then what we could do from that open loop characteristic is come up with our closed loop transfer function, as shown. Again, leave it to you as the exercise for coming up with that closed loop transfer characteristic. Now what we want to do, instead of, previously we had this gain, K term, in our system. But now what we want to do is isolate our P1 term, our pole, isolate that, and then kind of redo our root locus, and then vary the pole location, P1, as our parameter as we look at our root locus. So how we're going to do that is we're going to rearrange our closed loop transfer characteristic into the form of 1 plus P1 GH. So before that was 1 plus K, the gain, because we were varying that gain, times GH. But now what we're going to do is isolate that pole, that P1 term, and vary P1 to look at our root locus characteristic. So how do we do that to isolate that term? We take everything in the denominator that doesn't have a P in it and then divide. So notice what we did here is we took that term and divided the P term by there. But whatever we do to the denominator, we have to do to the numerator. And so that's what we're doing right there. And then so the resulting open loop characteristic from that system is exactly, let's get rid of some ink here. Okay, it's this term right here. Okay, this term right here is our resulting open loop loop gain. Okay, the equivalent, what we previously called KGH. Okay, so we have that characteristic right there. And now what we can do is instead of varying K like we've done previously, we have P1, that pole, as a knob we can turn to see what happens. And so what we're going to do is look at this characteristic down here, and when we solve that, we're going to see, first of all, s plus 2. We have a 0 at -2, and then the original starting point, we can use the quadratic formula for that, substitute the two values of s, and we're going to get those as our starting point. So here are our poles. That's essentially our starting point. And then as we vary P1, what's going to happen is, remember what's going to happen. So K equals 0, we start at the poles, and then notice the trend. It's going to go away from the poles, hit this axis, and then go towards this finite 0, and then this way off to this sort of infinite 0 over there. So now, again, we could vary that as a function of P1 and get a desired characteristic for our system that is, again, whatever our goal is for that system. Okay. Next, we're going to look at the root locus for a positive feedback system. So today, everything we've looked at had a negative sign right there, but now we're going to have a positive term right there. So one way to do this when we come up with our closed loop transfer characteristic, it's going to look the same, except that term there is going to be negative. So one way to think about this, if you want, is again, if you want, you can make that term negative and then make that sort of a negative HS. So you can think of it as subtracting negative HS as an alternative, and then sort of this, you don't have to worry about, think of it as a positive feedback system. But however you want to think about it, it works well. However, now when we look at the condition for the existence of the pole here, now when we set this equal to 0, look what happens. We move that to the right side equal to 0, and essentially that term becomes an equal sign. So before that was equal negative 1, now it's just equal to 1. And so that means it's a magnitude of 1 at an angle of K360, or essentially the no phase shift. No, before it was 180 degrees. So again, if we had a sine wave, it was negative of that, so it was 180 degrees out of phase. In this case, it is not out of phase based on the 360 term that we show there. So that's a critical difference with a negative and positive feedback system. Now, what we did was we looked at some of the properties of root locus when we first talked about it. We talked about number of branches and symmetry, and what you'll see for those definitions is the same conditions apply as we had for negative feedback system. Now, for the real axis segments, I would ask for you to go back and look at this definition for the negative feedback system and compare it to here. Was it to the left of an even number, or was this an odd number? So I will leave that for you to go back, through your notes and see the key differences here between the positive feedback and the negative feedback. Okay, and so kind of go back and look at that. Similarly for the starting and ending points, in this case, root locus begins at finite and infinite poles, same, and ends at finite or infinite zeros. So that looks very similar to the negative feedback case. And then finally, the behavior at infinity. So root locus approaches the asymptotes as the locus approaches infinity with this intercept and then this angle. So again, go back and you can look at this. The denominator looks the same. And again, all the poles and zeros look the same as well. Now this term right here, because before when this angle term was an odd multiple of 180, this term was a little bit different. But now because of the 360, so that's a difference with the negative feedback. So a lot of similarities, but a couple of small differences that you can go back and kind of compare with the negative feedback system. Next, we want to get into what's called pole sensitivity. So as we look at our root locus and we're varying gains, etc., how sensitive is our pole location relative to small changes in gain. So we maybe have selected a gain and we want the poles at a very specific location. However, if we build this in analog or some temperature variations or with some aging, something changes here. What happens as that gain changes small values over time? What happens to those poles? Okay, is it going to be a major change or a minor change? Something very good to know. Now we have looked at sensitivity previously, typically with regard to gain, but we'll look at it now relative to the pole locations. So really, it's the relationship between gain and pole locations, and it certainly is a nonlinear relationship, as we'll see shortly. Okay, so similar definitions of sensitivity that we've seen in the past. So given this system here, what we want to do is find the pole sensitivity at two different pole locations right there. So what I've done is we've seen this in previous modules here. And so as I vary my k from 0, in this case to 50, I want to look at these two pole locations that I've shown here and here. Okay, so we have seen this in previous modules, so I don't want to go through and derive that. But now in terms of looking at the sensitivity here, so essentially what do we need to do? If we take the denominator here, differentiate that with regard to k, we're going to get this expression right here. Now our goal is to rearrange terms and solve for that because that's what we're looking for right there. And so walk through that and you'll see this rearranging of terms leads to this expression right here. Now, in terms of the sensitivity of that pole location as a function of the gain parameter. I have my K over S term times this term right there. So I can have an expression now and see what sensitivities that I have. So the first one we're going to look at was this first pole. Okay, and that first pole had a gain of 5. So we're looking at this first condition right there. And so what we do, we can substitute that K equals 5 there, the S there, also there, and we'll come up with this sensitivity value, which comes out to be negative 0.059. So we have that value. Now let's clear some ink. It's getting a little busy here. Okay, so we just calculated this value, again, by substituting K there and the value of S there and there. So that gave us this value, which is here. Now what we want to do, okay, that value is right there. Okay, now what we want to do is say for a 10% change in K, okay, so this term, this delta K over K, is essentially now 0.1. So for a 10% change in K, what's going to happen is we're going to look at this sensitivity, and so what happens is this delta S now will result in 0.056. So if I look at this pole location right here, which is at negative 9.47, if my gain changes 10%, what happens is that delta S is positive 0.056. So I'm at negative 9.47. That pole's going to move slightly to the right by 0.056. So, you know, not too bad, not overly sensitive. You know, a 10% variation in the gain, a very small incremental delta in that pole. So we could say not too bad, not too sensitive. Now what we want to do is look at this pole for a gain of 50. So what we're going to do is plug in, let's erase the ink. Okay. Now what we're going to do is we have a gain of 50. We're going to substitute that gain in for there. And then our pole now. So now look, we have a complex, okay? We have a complex pole. Has a real and imaginary term. So as I do the substitution, now when I substitute that in, notice I'm going to get essentially an imaginary, a real and imaginary part. So I can write that in terms of like a polar notation. So I have a magnitude. The magnitude is 1 over the square root of 2, and that's going to be at an angle of negative 45 degrees. So that sensitivity now is this right here, and also for a 10% change in K. So this term right here, okay, is now essentially 0.1. So as I make that change, what we're going to see now is my pole location is changing by minus J5. So that's a pretty big change in pole location when my gain is high. So the result here for this particular system is the sensitivity of that pole location is much, much greater as the gain gets larger. Again, when the gain was small, 5, very small incremental change in that pole location. Same change, 10% change in K, when we're at a much larger gain, has a much bigger impact on that pole location. So again, if you have a system with a very large gain, and that gain can change over time due to aging, due to heat, due to other conditions, you have to be very careful, because what can happen over time is if your pole location changes, and again, you might change damping, right? So the damping might get worse, may have more overshoot, or some other factors as well. The settling time might increase. Something may change in your system, and so you may not get the response that you think you're going to have maybe when it first came off the production line. But maybe 5 years down the road, again, there's a condition where the system wasn't as good of a design. Again, more overshoot, more settling time, something, and so the system would deteriorate. So it's very important to know as you go through these systems that things can change over time. And so that's why it's really good to do sensitivity analyses here. And again, what I will say is there's definitely this nonlinear relationship, usually at the higher gains, that you need to worry about as you go through this. Okay? So that will complete this module. If you have any questions on any of this material, please don't hesitate to reach out. Thank you.